Okay, does anyone need more time to get there? Great. So again, here is the base graph for an exponential function. F of x equals b to the power of x for some value of b. So let's, we okay? Yeah, cool. Let's put that directly into Desmos. So we're going to go f bracket x close bracket equals, now type in b, and to get to the power of, you can go shift 6. And it does that, that's shift 6. If you forget that, there's a little keyboard down here that you can use as well. And then you're going to put in x. Now, when you do that, you can see that Desmos gives you the opportunity to add in a slider, i.e. it's assuming that x is the variable, which it is, and that f is the function, which it is, and it's saying, oh, is b a number that might just change? So tap on yes or tap on b to add a slider. And now we have the function f of x equals 1 to the x, which is pretty boring. It's what? It's trivial. You can make b whatever you want to, but eventually, but just, I reckon, start off with b equals 2. It kind of is a decent looking graph in the window that you've got, whereas if you make it too big, then it tends to be too steep. Now, the first thing to point out, oh my gosh, there are so many different little complexities with exponential graphs. I want to keep it simple. So I think it's going to be a little bit like physics or something like that. You know how like you're given a really basic model of the universe, and then as you go up the levels of physics, you get more complex. It might be a little bit like that. So I might just touch on things and then come back. So just to remind you that when b is bigger than 1, it's a growth graph. You can play this yourself, and when it's less than 1, it's a decay graph. And if you know your exponential laws, you'll know why it suddenly flips. Okay? If b is less than 1, it's not well defined. And you might get dots, or you might get nothing, like this. If I zoom out, will I get dots? No. So just be mindful that for the purposes of this, I'm going to use b equals 2. So it's a whole number that's bigger than 1. If you go for a fraction, it'll flip everything around, and I wouldn't call that the base graph, although it is. But yeah, but I'll explain more later. Okay, so what we're going to do is we're going to play around with transformations of the exponential graph. Now, raise your hands if you've heard the phrase transformation before. I'm not going to quiz you on it. I'm just wondering who can remember or who has that access to that. Okay, hands down. So, in functions, we didn't do this as part of function study because I want to just see it through different kinds of functions. In functions, there are transformations that you can make to the base graph to create a brand new graph. So, for example, 2 to the power of x could be turned into 3 times 2 to the power of negative x plus 4, and then subtract 7 from the whole result. That's a transformation of the base graph. Okay? It's when you're doing something to it. There are 3 categories for transformations. There are dilations, and you'll see the graph stretch or shrink away or towards the axis. There are reflections, which are mirror images across the x and y axis. And there are translations, which are vertical or horizontal shifts, either left, right, or up, down. Now, what I'm going to ask you to do is this is where I was just, I'm making it more exploration than me just demonstrating, is I'm going to get you to play around with the base graph that you just put into Desmos to see what happens with it. And I've asked you to consider the following things. What happens to the shape of the graph? What happens to the asymptote? And what happens to the y-intercept? It may be nothing, it may be something, but it's your job to figure that out, I guess. Okay, so shape, asymptote, and y-intercept. I'm now going to zoom out, and you can see on the first page I've got dilations and reflections, and on the next page I will have translations. Now, even if you're a methods kid an extended kid from last year, the number of transformations you have to be across are more than they were in extended. Okay? You tended to use transformations of quadratics, which tend to be reasonably boring. In this particular course, we look at all kinds of transformations. So I'm going to get you started, but I don't want to lead you too much because then it just becomes one of those demonstration lessons. So if we have a look at the dilations, for example, I've got there what I want you to do. I hope that's not too small. In the red there, it tells you how to experiment. Experiment with positive values, experiment with big and small values. Okay, so don't go negative, and the reason why is because reflections are negative. So dilations are only about the size, not about the direction. And you can see here that I've got two forms that create a dilation. Either the base graph is multiplied by A, or just the X coordinate is multiplied by A. Now, I'm not doing this for all of it. I'm just doing it to get you started. What you can do, for example, is you can just put numbers before B, go, well, what happens if I make it 2B to the X? What's happened to the Y-intercept? What's happened to the shape? And then 3, and then 4, okay. And then what's happening with 0.5? Oh, I see. So you can start experimenting with it a bit. Zooming in and out of the graph is probably a useful thing to do. But you can also just choose another letter like A and add the slider in like so. And now you can actually play with it like this. So in this instance, I'm just going to do it roughly. You can do it properly. You can see that as I make A bigger, the y-intercept is going up the y-axis, yeah? So see if you can get a relationship there, what's happening. But also, in terms of dilation, this is the hard thing to see in an exponential graph in a way. But can you see that the graph is actually getting closer to the y-axis? It's kind of shrinking to the y-axis. So that's what the dilation factor does. So a big dilation factor of 7.5 makes the graph cling more closely to the y-axis. And we call that a shrink towards the y-axis, or dilating towards the y-axis. And then you can see what happens when A goes below 1 and see what happens then as well. So play around with that. I'll very briefly go through the other ones, but not in Desmos. With the reflections, there's only one thing you have to look at for it. So once you've done that, if you've got A still there once you finish playing with it, either delete the A or bring A back to 1 so it's having no effect, right? So when A is 1, there's no effect there. Remember, you're going to have an A there, and then you're going to move the A up there. So there's a couple of places for it. It's written right here, so you're okay. Here, you can see my base graph just has a negative there or a negative there. Okay, so that's why I don't have any comment. And the next page, when I get to it, would have been smart if I put all these on the same page. The next page is translations, and you can see that I've got, that's K by the way, the base graph plus K added to it, or I've got B to the power of, and then H taken away from the X coordinate. And it said, and I've said here, experiment with positive and negative numbers. Okay, so it's about you putting down dot points next to each of the transformations to say what you think is happening. You could put it straight into your summary book if you're feeling confident, or you could scribble it down in your bookwork, and then we can discuss it a little bit later. So I'll put translations up in a second, but I'll move it back to the other two so that you can start with those. Is that enough of an idea to get going? So it's playtime now. So I'll pause the video and start using Desmos to play around with it. If it's a technical problem, come and ask. Oh yeah, also look at the asymptote, what's happening at the asymptote as well. Okay, playtime. What how people are going? Okay, so we'll go back to the dilations first. Basically, I started you off with the hardest one, and then I left you with the easier one to see in an exponential graph. So what did people notice? When I multiplied b to the power of x by a, what happened? You don't have to have it in fancy language. Thank you, Lily. So the bigger a is, the closer to the y-axis. It's hard to see, but that's basically what's happening here. So if I zoom out, the problem with an exponential graph, and I say problem, but it's not its fault, is that because it's got an infinite tail off to the left, it's hard to notice anything happening on the left. So you're really looking at the right here. So as I make a closer, can you sort of see that it's sort of reaching towards the y-axis? So as a gets bigger, it shrinks towards the y-axis. And as a gets smaller, it stretches away from the y-axis. And that has an impact, of course, on the y-intercept. Arif? Yes, good. So let's write that down. So what happens? Let me switch over so we can see that. So what happens? The y-intercept is 0, a, and that makes sense, doesn't it? Because b to the power of 0 is 1, so a is now going to be a times 1, which is a. Why is it just 0, a? As a increases, it stretches away from the y-axis. I do not have enough room here to write this properly. As a increases, it stretches away from the y-axis. If a is less than 1, it shrinks towards it. I'm so sorry about the small writing. Is that okay with everybody? These notes will be available on Google Classroom, guys, because, yeah, I'm going to be switching between screens a bit. What happened when we multiplied the x coordinate by a instead? Elizabeth, what do you notice? It's hard to see. Did it have any effect on, let's start off with the start. Did it have any effect on the y-intercept? It didn't. Good. Your recollection is correct. Because if I've got, so the y-intercept is at x equals 0, right? So if I multiply 0 by a, guess what? Still 0. Okay, so it won't change the y-intercept. Did you notice anything else, Elizabeth? Just putting you on the spot. Yeah. Okay, let's have a look at it. So it does affect it. First of all, as I increase, I mean, if I just zoom up on it, pop this down. There we go. If I zoom up on it like so, there's the y-axis, the y-coordinate here. Sorry, the y-intercept here. And we can see that it's not affecting the y-intercept. So that was good recollection. The steepness of the curve is absolutely spot on. You can see that basically what I'm doing is I'm taking the old input value of x and I'm increasing it by a factor of a, right? Now have a look to the left and to the right. As I make I'll go a fractional first to start with. Can you see how that graph is lifting away from the x-axis? So again, it's a dilation where the graph is stretching away from not the y-axis, but the x-axis. The impact, as Elizabeth said, was it affects the steepness, which is true, but if I go out far enough, you can't see it as much. It kind of just jiggles around a little bit. It's still quite steep because actually what's happening is it's accelerating faster, and so it's moving away from the y-axis, so the x-axis faster. So when A is between 0 and 1, we've got this thing where it's stretching away from the x-axis. So stretching, which is the faster gradient that Elizabeth was talking about, plus stretching away as a result. And if A is bigger than 1, so the bigger A is, the more, can you see how between, just look between -5 and 0 here. Between -5 and 0, can you see how it's almost flattening? It's like it's laying it down. So it's actually shrinking towards the x-axis. Okay, but again, it's still sticking right there. It's firmly bolted. The y-intercept is firmly bolted. So let's put something like that down. Got a bit more room this time. And the y-intercept is unchanged. Okay, so that's dilations in a nutshell. It stretches a graph. You know what? I'll quickly show you this because it's so hard to see. Yeah. Yeah, it does. Yeah, which is why we'll talk about that in a second, but there's a reason why it works opposite, which is why I'm just leaving B at 2 to keep it constant from that perspective. So if I put A here, you can see it really well with the parabola. It's harder to see with an exponential, but can you see what happens? It's shrinking towards the y-axis, and then it's doing that. It's getting fatter when it's a fraction. But if I don't know how well this will work. If I do it this way, so oh man, ax to the power of 2. This might be hard to see, but it's sort of flattening towards the x-axis, and then pulling itself up as I go. Yeah. Anyway, that's just f of x. That's just a parabola. Okay, so that is dilations done. It's a stretch factor. So they're a shrink or stretch. Next thing I ask you to do is to look at reflections. This is a bit more straightforward. Parav, do you want to say what happened when you reflected by putting a negative in front of the B? That's fine. What did you observe? What did you see? Be as basic as you want. Yep. Which way? Opposite. Opposite. Yeah. Orientation flipped, didn't it? I like the word flip, or reflects the technical word. I'll get rid of the A, and I'll turn the graph back on. So we can see that when we put a negative here, yeah, the orientation just flips. So it's like a mirror, where the mirror surface is the x-axis. The plane of mirror is the x-axis. And I'm just going to put down how you say that. You just simply say, reflects about the x-axis. Done. Now, please remember that negative b to the power of x means b to the power of x, make it negative. It doesn't mean take negative b and raise it to the power of x. Okay? So order of operations is important. BEDMAS says, let's call it BEDMAS since we're using exponents. BEDMAS says exponents before multiplication and division. Okay, so the x belongs to the b before it belongs to the minus. Okay, and I'm hoping that kind of makes sense to you. We'll look at it more formally as we progress through the year. But basically what we're saying is that the old function was b to the power of x, and we're just changing every single value to a negative value. So it reflects. And what do we have with b to the negative x? Zoe G? Flips on the y-axis. Perfect. So there it is there. So we've got without it and with it, and without it and with it, and without it and with it. So it's exactly the same shape though. It's just that it changes direction effectively, doesn't it? So we say flips or reflects about the y-axis. And that's it, 2 reflections, okay? So we've got a reflection this way, and we've got a reflection this way. It swivels, it orientates, it effectively mirror images itself. It mirror images itself. Any questions? Okay, so that's reflections out of the way. The last one, or last set, so you can sort of see they pair up, they have very similar behaviors. It's just either up and down or left and right, really, either vertically or horizontally. So what about b to the power of x plus k? Siggy, what happened when you added a value to the end of b to the power of x? Shouldn't have done that. Oh, okay. Yeah. Yeah, if you do too many values at once, then you'll get lost with what's affecting what. So it's always important to go to the base graph and then do it in isolation so that you can see exactly what's happening. William, what about you? What did you have for adding k? What did you have when you added k? Didn't get that far. No worries. I'm not trying to pick on people. I'm just picking people at random. Arit, go for it.
So in that case, k was the asymptote, the horizontal asymptote.
That's true.
That was the main observation.
Good. Yeah. There's one other observation, which is I think you would agree would be basically it as well. A more basic observation in a way, and that is that as I made k bigger and positive and negative, well, as I moved k, in fact, the whole graph goes up and down. Again, it looks like as if it might be changing size or something like that, but it really is, if you zoom out, it really is just the same graph going up and down. Yeah, and this is where you can go y equals k and play around with it to change it so that it's a dotted red line or something like that. I'll change that color to blue, to purple, so it's different. So you can sort of see here that this is the asymptote. And that as I move k, the asymptote is changing as well. So when k is positive, it lifts the graph up, and when k is negative, it drops it below. And it means the y-intercept is increased or decreased by that number as well. Yeah? Is it okay? Okay, cool. So if k is greater than 0, graph vertically shifts up. And if k is less than 0, graph vertically shifts down. So translations, I'll just zoom out a little bit so we can see the whole thing. So translations is the fancy word. To translate means to shift from one spot to another. Like for a language, for example, when you're translating a language, you're shifting from one word in one language to the same word in a different language or sentence or structure or whatever. So translate means to move. So you can call it a vertical translation, or slightly less fancy but more easy to understand is to say it's a vertical shift. Okay, what about H? What did H do, Zoe A? Yeah, it's a horizontal shift. Yeah. So where adding K was a vertical shift, subtracting H did a horizontal shift. Why did I say X minus H instead of X plus H? Did anyone figure that out?
If you put plus k, then if you put a plus, then it'll just increase the value of x. If it goes up 2, then it'll just be raised to the power of 3.
Yeah, the reason why you're right, and you're right. Turning point form or vertex form. They're just translations, right? They're just translations. So yes. Visually, there's no reason to do it really, other than visually. Normally, we associate a positive value with going right and a negative value with going left. So we write X minus H because when H is positive, then it goes right. But do note that if I had 2 to the power of X plus 3, it'll go left. It won't go right, because plus 3 is 2 minus positive 3. So it's going to go 3 to the right. I don't know whether it's actually easier to put it as X minus H. There's a confusion somewhere, usually with someone. So yeah, I'll just do that. I know that you've done it already, so just really briefly, put an X minus H with a slider, and we can see if we have it zoomed out. Oh, thank you. Not taking my own advice, am I? Okay, so as I slide H, it kind of looks like as if it's the same as the dilation, so it's a bit tricky to see, but it is actually the same graph, just moving acrossways or that way. It's not stretching towards the y-axis, it's actually just moving. The whole graph is moving to the left or moving to the left or moving to the right. So if H is positive, it moves to the right. If H is negative, it moves to the left. So it's a horizontal translation. Okay, let's capture that. So I guess the thing to note is that when you are affecting the X value, it kind of has a counterintuitive result. So X plus 3 will move it to the left. When I raise b to the power of 0.3 of X, it makes the graph wider, not thinner. So it feels like, oh, 0.3 is a fraction, smaller. It should shrink it, but it doesn't. It actually stretches it. So it's counterintuitive when you're looking at the X values. So if H is greater than 0, I might just even summarize it a bit more. Horizontal shift right. If H is less than 0, horizontal shift left. And I haven't captured every single detail. So for example, it means that the y-intercept would also go If I zoom in, so there's the y-intercept. Oh, this is bad. Where's B? 2. Why is that not hitting 1 there? Oh, because it's a horizontal shift. Yeah, so it does move all the values over to the right, which is why, hang on, let's see if I can get something like this. So when h equals 2, now the graph function is equal to 1. So if I sort of go, no, I won't do it because it's too confusing. So you can see that if I make h equal to 0, there's the coordinate 0, 1. That particular coordinate there, if I go h equals 2, 1 is now at 2. So everything has been translated over to the right by 2 units. Okay, so that's a bit tricky, isn't it? So conscious there's only 3 minutes left and it's your second last lesson. So really briefly then, these are a set of transformations that we're going to be using over and over again. And the point of the transformations is that by applying a bunch of transformations, we can get a brand new graph. So if I choose something like y equals 3 multiplied by 2 to the power of x plus 1 plus 4, I can take my basic graph and I can say, well, it's gone up 4 units. It's gone left 1 unit. And so it's going to be like this instead. Then I can also talk about the fact that it hasn't reflected at all. It's also got a dilation of 3. And so I can start creating a brand new graph by considering the transformations rather than plotting it out. So what does that mean? Next lesson. I hope that was worth it to sort of get a sense of the transformations. Next lesson, which is next term, I know. So I'm not giving you any homework other than to have a rest for maths. Next lesson, we are going to go through this in more detail where I show you how you can take the base graph and, given a new graph, apply the transformations to create a new sketch. So that's what we'll do next lesson, plus solving a few different problems around exponential functions, and then we'll go from there. That'll do. I'll stop the video.